Hi, hello, how are you? Craig Chapman here with part 5 of experimenting with neural network simulation. In this part, we're actually going to implement the backpropagation algorithm, and then we're going to take a look at a possible training example or two. But before we get started, back in part 4, I did have an error or two for which I've gone back and re-edited the video to correct, but I'm just going to share that correction with you in case you haven't seen the replacement version. So on this slide, I had the equations dh11 through dh22, and each of these equations was referencing n1 or n2, when in fact they should have been referencing de1 or de2. The numbers that you see on the screen are actually the correct outputs for the equations if they are the correct equations. So a little error in the typing on the slide there, but that's the correction for you. Okay, so let's take a look at the implementation of the backpropagation algorithm. Now, I've actually gone ahead and written this algorithm already because I did try to record myself doing it 2 or 3 times and got quite confused, and so I decided better to just write the algorithm and then show you what I'd done. So here I have a new method on our iNeuralNet interface. I've actually added 2 new methods, temporary hardcode weights and train. Now, I'll take a look at temporary hardcode weights first. You'll remember that when we had our query to the network previously, we were hardcoding weights for our example. Well, I moved that out into its own function here. The reason that I did this is because we need to query the network before we train it. And if we try to do multiple iterations of training, then each time we do, the weights will be overwritten by these hard-coded values. So I moved them out into their own function, and then in the forward-only application, I actually call temporary hardcode weights before calling to query the network. Another thing that I've done is in our neural network types unit, I've changed the axon value from single to extended, and this has helped to resolve some of the rounding issues that I was getting using the single type. Now, because I've used t-axon value just about everywhere in the code, simply changing the data type here means that it's now changed throughout the code. So everywhere where we were using a single before, we're now using an extended. So let's go and take a look at the implementation of the train method. If I take a look at this, the first thing I'm doing is putting in input values and getting target values back. So I start by querying with those input values, and I store the results in this local results array right here. Then I'm going to step backwards through the layers, and for each layer I'm going to calculate the error and the error gradient. Now, I've actually skipped a step here, which I'm going to point out in just a moment, but for the first layer, with the first layer going backwards, so our output layer, what I'm doing is I'm testing to see if this is the output layer, so that's pred of layer count, and then I'm looping back through each of the neurons, and for each neuron I'm calculating the error amount, which is our target value less our output value, and I subtract that from 1 to get the error amount. And then also calculating the error gradient, which is how much does this neuron need to be adjusted, or this neuron synapses need to be adjusted to account for the error on this neuron. Now, for the neurons in the remaining layers, I'm calculating the gradient, so I'm starting with a gradient of 0. I'm looping through all of the neurons. Now, you can see here I'm looping through the neurons in this layer. I'm now going to loop through all of the neurons in the next layer because I'm interested in the synapses that connect the next layer to this layer. So I'm then looping through the synapses in the next layer, and if the axon index is pointing at the index of the current layer, so in other words, if this is a synapse which connects an output neuron to the current neuron I'm inspecting in the hidden layer, then we'll calculate the error gradient, and I'm just using the equation that we saw in the PowerPoint for do that. Now, what I'm not doing here is I'm not calculating the neurons.error for this particular neuron. So I'm not calculating an error value, I'm just calculating the gradient. If we had a multi-layer perceptron, then I would need that error value, but for the moment I'm just assuming, for the sake of keeping the code simple, that we are dealing with a 3-layer network and we're in the hidden layer. So that's running that calculation through there. Now, those 2 values that I'm calculating, the error and the error gradient, I've added onto our data type for the neuron. So if I come and take a look at t neuron, I've added error and error gradient, each of which are axon values. So effectively I'm able to pass the error and the error gradient back through the network. For each layer in the network, I can use the values in the layer in front of it to calculate the values for this layer. So once I've calculated the error and the error gradient for each of the layers, I'm then doing a second pass backwards through the network, and I'm adjusting the weights. So again, I'm checking, am I in the output layer? Because if I'm in the output layer, then I simply do the current weight less the error multiplied by the gradient multiplied by the axon value of the input to this neuron, so the previous layer axon. And then I multiply by our learning rate, which is a constant in the code. I'll go and pull that out. It's 0.500 here. And actually, I'm going to go ahead and pull that constant out of this method now, and temporarily we'll put it up here so it is global to the unit for the moment. So I've got that hard-coded learning rate, and then if I'm not in the output layer, well, the calculation's a little more involved. As we saw, I'm taking the axon value that we are connecting to by this synapse, I'm multiplying that by the error gradient, and then I'm multiplying by the net delta of that axon. So that's how I'm doing that, and then multiplying by the learning rate. So if I run through this now on our forward-only application, what I've done is I'm still doing temporary hardcode weights. I'm querying the network and writing the output. I'm then calling our train method to train the network with the target values of 0.01 and 0.99. I'm then taking the output of, or rather setting the output to 0 and querying the network again. And then I'm going to output the values post-training. So let's go ahead and run the application and see what we get. Oops. Make sure the application's selected. Let's do that. And you can see that our first pass we're still getting 751365, 772928, and our second pass we're getting 742088, 775289. Well, how does that compare with our example from last week? Well, if we take a look at the slide for the output last week, we can see 742088 and 7752849. So we are actually getting the correct values coming out here. So our network is now trainable. So before we go any further, what we should probably do is give ourselves a way to calculate the total network error at each iteration of training. But I'm going to do a little refactoring to this code first. So the first thing I'm going to do is have a procedure output, let's say results, and then we'll put in an array. So results is a t axon value array, and we'll put in a total error parameter, which is a t axon value. So what I'll do is I'll take our little write lens here, oh no, something went wrong, and the for loop, and let's paste these in. Okay, if length of output values is 0, something went wrong. Well, this is no longer output values, this is results. Length of results. And we're using an IDX index. Output values results. And then we'll bring our IDX into this method. And finally we'll add writeLn total error, and we'll put our total error value in. Okay, so instead of, after having queried the network, instead of writing the results out directly, we'll do output results, and we'll output values. And for the moment, 0, because we haven't calculated the total error for our network yet. Let's bring these variables down a little. And before I go any further, there is one other thing that I forgot to mention. You'll see that I'm actually only using one unit here now in the forward-only application, and that unit is AI. That's because to the package I added a single unit, unit AI, and it doesn't seem that it's in here, so let's go and add it again. There we go, AI, and if I take a look in that unit, I'm just aliasing all of the types that we use in our forward-only application, and then I have a function which is going to create an iNeural net, and the iNeural net will be a t-perceptron type. So now if we come and look back in the application, you can see I'm doing net equals perceptron and using that data type, and I'm just using that one users. So forgot to mention that, so let's carry on with refactoring for our output results. So now we train the network, and then actually I don't think I need to change set the length here, so I'm just going to query the network one more time, and then I don't need all of this because once more we're going to output our results like that. So let's go ahead and build all of that up. And you can see our total error is coming out as 0, and we have the results for each frame of the network. Okay, so now what we need is a way to calculate our total error. So let's go and add that to the code. And I think the easiest way to do this is going to be, let's see, function. We should have a function rather. Function total error, and this will be a t-axon value. Now in order to calculate the total error, we need to know what the target values are, so we'll pass in target values t-axon array. Okay, so I think that'll be our method. Let's go ahead and add that to our interface here. So now if we come back and implement this, total error, so t-axon, that's actually a t-axon value array, so I need to correct that everywhere. Let's do that real quick. T-axon value array. Okay, so to calculate our total error, how do we do this? Well, we need to loop through our output values. So we're going to have, or our output neurons rather, and so we'll have neuron IDX is a tnet index, and then we're going to do for neuron IDX is equal to, from layers, we want pred of f layer count, so that gives us our output layer dot first neuron. I'm going to take a copy of that to last neuron to begin, and let's have an IDX tnet index, and we'll set IDX is equal to neuron IDX less the first neuron. So this will give us a 0 based IDX here and an IDX here based on the output neurons. Okay, now for the output neurons we want to get the output value. So we're going to say f neurons, actually f axons, and then we want f neurons for the current neuron IDX dot axon. I believe that's right. So is that going to give us the, let's have a look, tnet index? Yes, that's going to give us the index of the axon that we want, and we're subtracting that value from our target. So we're going to say target, target values IDX, because that's our 0 based index, less the axons. Now that value is, this is going to be a sum. Okay, so we're going to do, let's see, delta is equal to that value. So that's our actual delta value. Delta will be a t-axon value. And then we calculate the error for this particular neuron by doing delta times delta, so that's delta squared. And then we multiply the whole thing by the learning rate. Okay, and we need to add that value to a running total. So we'll say result is equal to 0. Actually, let's put 0.0, help the compiler out. And we'll do result is result plus that value. So by summing that up, we should get the total error as a result. Let's go and see if that works. So what we'll do is we'll say total error, and then we need to put in our target values, which are 0.05, is it? No, 0.01 and 0.99. So those are our targets. Make sure I get commas and periods and everything in the right place. And then that would be a function of net.total error. And that is a method. Okay, so that is the method that we want. And then we're going to do the same thing here where we output these results, get the total error once more. Let's see if this builds, because it doesn't seem to be happy about total error. But it has built, so let's see what we get from it. Okay, so in the first instance we get a total error of 274811, and then we get a total error of 267976. And I can tell you from looking back at the previous slides that that is incorrect. So I've got something a little bit off here. Let me go ahead and check what I've done. So I'm going to run through one more time with a breakpoint, and we'll breakpoint. And now I see my silly error. I've got first neuron to first neuron. We need last neuron. So let's go ahead and try running that. 29837, good. So we have a successful demonstration of the error value here. So we can see that the error value has changed from 2983771 to 2910277. And if we take a look back at the slides from last week, we can see those values here, 2983711 and the new delta 2910277. So we know now that our network is doing as it should during a training cycle. Okay, so now let's take a look at running the network with multiple iterations of training. And the way we do that is very simple. We'll just do, say, for IDX is 0 to, let's say, 100,000 iterations to begin. And we'll run train 100,000 times. So building and running this result, we need IDX. IDX in this case can be a simple uint32. And what we're actually seeing with the output now is the result here, 0.01 and 0.989. Well, our targets are 0.01, so we've got that coming out with relative precision. And we've also got a target of 0.99, well, we're getting 0.9899. Let's go ahead and run this an additional 0 here and see what we get. 0.01 and 0.99. So although the error calculation kind of freaks out here, which you would expect as we approach 0, we actually are getting the outputs that we want from our network. Well, since we know we can do that, we can actually optimize the training a little. And the way we do that is for each time that we train the network, we want to query it again. Let's say 0.05 and 0.1 as our input values, and then our output values we just store off. And then we're going to get the total again. So what we'll do is we will repeat this training exercise until the net total error is, let's say, less than 0.001. Maybe that will work. So let's go ahead and see if this application runs. What could happen is if we don't achieve this error ratio, then we'll just get stuck in this loop. So let's find out what happens when we run it. There are errors. Total error. I need to give it total error for the target values. And it does indeed complete, and it completes. We're still not quite at our result here, so it completes a little early. So let's go ahead and reduce the error that we want. And now we're looking very close. Let's reduce the error a little bit more. It doesn't look as though we're going to achieve a precise training value, but we are getting incredibly close here. So we can see that if we train our network over successive iterations, that we do get to an approximately correct output. I don't think I'm going to punish the CPU anymore with this. So let's consider now taking a look at another example. So what I've done here is I've created a new program named binary counting. And what I'm going to do is teach our neural network to count in binary. So to do this, I'm creating a perceptron with 3 neurons in each of the 3 layers. Now I've added a parameter here, and you can see I've put 1.0, 1.0, 1.0. If I go and take a look at the perceptron function, you'll see that this is an array of biases. And if we go take a look at the perceptron code, at the T-custom neural net code, you'll see that in the constructor I've added this biases array, and then within the constructor I've added this initialize biases to the biases that we pass into the constructor. And then if I go and look at the initialized biases, you'll see that I'm looping through setting the biases to the values that I pass in. Now, I didn't end up needing the biases for this example, but going forwards it would be useful if we could set the bias values without having to call this temporary hard-coded function. Let me find it, this temporary hard-coded weights function. In fact, I'm leaving the temporary hard-coded weights function in this code because I'm providing you with the source and I'd like you to be able to reproduce my results. But we don't actually need this anymore. This needs to be removed because we shouldn't be hard-coding the weights into the network. And as you'll remember, this includes weights plus biases. Now without this function you'd have no way of reproducing my results, so I'm leaving it in. But for the binary counting example it's not required. What I've done here is put in 3 biases of 1.0, which means effectively all of our layer neurons are going to get this input of 1 on their bias neuron. Now that really isn't going to change anything. By default the biases are set to 1 anyway, so we can safely ignore these. But for the sake of this demo, I'm just going to pass them in. Now what that means is that to set up our forward-only example, in order for that to build, I'm going to have to add the same biases to it. Now if I add the biases 1.0, 1.0, 1.0, so that's 1 bias per layer. Make sure I type that correctly. What's going to happen is those 3 biases are going to be set, but then almost immediately afterwards they're getting overwritten in this hard-coded function. But at least that means that our forward-only example should build again, and if we go ahead and run it, you'll see that our results are the same as they were before. So, coming back to the binary counting demo, what am I doing here? So I'm creating our 3x3x3 perceptron, and then I'm setting up a number of iterations for training. In this case, what have I got here? 1,000,000 iterations for training this network. And each of those 1,000,000 iterations is going to go through, or 1,000,001 since it's indexed from 0, it's going to go through inputs 0 through 7, and it's going to generate a binary input for our array and a binary target. So let's take a quick look at what this binary function is doing. It's taking the number that I pass in, and it's just looking at the first 3 bits, so the bit representing 1, 2, and 4. And if the bit is set, then it's passing in a 1 into our array, and if it's not set, it's passing in a 0. So effectively, the inputs to our array for this training sample are going to be the binary values 0 through 6. The training set, however, has this successor to the input. So effectively, if I pass in a 0 in binary, what I want to get out will be a 1 in binary. And then I'm training the network on that premise. So for every number I pass in binary, I want to get the next number back out in binary. So for a 0, I want to get 1. For 1, I want to get 2, and so on. Then after training the network for 1,000,000 iterations or so, I'm running through the inputs one more time. I'm going from 0 to 6. I'm pushing in the input and expecting as a target the same value as an output. In fact, the target value was here for error calculation. I no longer need that. So let's just push in the input. We push it into our array and we get our output values. Then I'm passing output values into this output results function. So the output results is just taking those 3 output values and rounding them, because remember we'll get a value between 0 and 1, and then converting that to a string. So we should get a 0 or a 1 for each of those 3, and adding the 3 strings together we get the binary representation of the number. We then use the same thing here, which is doing value 0 multiplied by 4 plus value 1 multiplied by 2 plus the value 2. So what we should get is in V the actual decimal value of the output, and then we're writing that to the screen. So let's go ahead and run this network. Whoops, wrong application. I want to build this one. And after a second or so of training, we get the numbers 1 through 7. So for inputs 0 to 6, we're getting outputs of 1 through 7. So that means that our neural network now is able to count. We're getting out 0, 0, 1 for an input of 0, 0, 0. In fact, perhaps I should put the input on the beginning of the string there. So let's do, yes, let's do this. Let's write to the screen. Actually, let's output results. If I call output results, but instead of outputting the results, I'm going to output the input array. Okay, that's not going to work. Okay, so I'm just going to push in the input array as well. So for our results, we'll have input, output. Let's do that. So in ARR, T acts on value array. So we'll have our input and our output values here. So this string is our output. Let's put together our input string. We'll do the exact same thing. So we'll have intstr, but instead of ARR, we're going to use in ARR for each of these values. And for the decimal calculation. And then we'll simply do a write. We'll put input plus s, so that will give us our string value, plus is equal to, and then we'll put in the int to str v to get our decimal value. And then we'll add a little bit of, in fact, let's just leave it there. And then for the output array, we'll add a little bit of space. Output plus. Okay, let's run this one more time. Okay, and after training, we can see for an input of 0, 0, 0, we're getting an output of 0, 0, 1. Input of 0, 0, 1, we're getting an output of 0, 1, 0, and so on. So for an input of 0, we get an output of 1, and for an input of 6, we get an output of 7. So we've effectively trained our network to count. Now let's just prove that that's the case by taking out the training section. So if I take all of this and I'm going to toggle the comments and run the network, you'll see that we effectively get garbage. We're getting 7, 7, 7, 7, 7. So we are actively training our network to count. Okay, so this video is going to include the source code for these samples. So you can go ahead and reproduce these examples for yourself. I'm not sure how soon I'll find time to do the next video. So my apologies if there's a delay. I'll try to get it out next week for you, but I just can't promise it with my current schedule. So watch this space for the next video where we'll take a look at parallelizing our neural network.